Hello and welcome to our video on an introduction to volumetric analysis. Today we'll be looking at why do we perform volumetric analysis and titrations in the first place, and then looking at the difference between the equivalents and the endpoints. This is a multi-part series on titrations as it's a pretty important topic in your senior studies. This video lays down the groundwork for why we actually do the titration. There'll be some other videos looking at graphs from titrations, and then another video looking at problems involving titrations. We'll do a separate video altogether on titrations as a practical and how you can master the technique of titrations. Before we get into any specifics regarding titrations, especially on how to perform them and how to interpret their results, it's important you get a good foundation on why you're actually doing them in the first place. Titrations are something that are really easy to wrap your head around, but just the whole process in which you need to do them requires a pedantic attention to detail. So you really need to pay attention when you're actually doing them. But that's a problem for later. Now we're worried about why we're actually doing them. At a very basic level, we use titrations to find the concentration of an aqueous substance. For example, if I were to give you a beaker of sodium hydroxide and ask you to find the concentration of it, it is likely you would have to perform a titration. Using this example, there are two basic principles you would need to use to do this titration. Firstly, you need a reaction that is predictable and that you, number one, know the results of, and number two, can control the results of. An example of this would be the acid-base neutralization reaction. We know for a fact that every time an acid and a base react, they'll give a salt and a water. As shown in the example, every time our base, sodium hydroxide, and our acid of choice, hydrochloric acid, react, they'll give the salt, sodium chloride, and water. Now, although we don't know the concentration of sodium hydroxide in this beaker that I've given you, we can work up a precise volume of hydrochloric acid that we know the concentration of. In our videos on how to perform titrations, we'll take you through how to do all of this, but just follow me for now for argument's sake so you understand why you're actually doing it. What we will then do is then add an exact amount of hydrochloric acid into the beaker of sodium hydroxide such that there is only sodium chloride and water remaining. So all the molecules of sodium hydroxide in that beaker I've given you have reacted with the hydrochloric acid that you've added. And you've added just enough, so there's no extra hydrochloric acid. There's only sodium chloride and water remaining. Now you might think, wait, you gave me a beaker of sodium hydroxide and you asked me to find the concentration, and I made you something completely different. How has that helped anything? However, we've actually done something incredibly clever here. We know the exact number of molecules of hydrochloric acid, for argument's sake, that we added into that beaker, and we know the concentration of the hydrochloric acid that we made up. We also know that that number of hydrochloric acid was exactly the same number of moles that were required of sodium hydroxide to fully react. Thus, using molar ratios, we can very easily find the number of moles of sodium hydroxide in that solution that I gave you. Then, if we know the original volume, so the amount of liquid, in that beaker, we can find the concentration. This will be a lot more simple in the next slide. Okay, so if you're a little confused, hopefully this will make things a lot more clear. On the left hand side, we have a quick diagrammatic representation of what a titration is going to look like. I don't want you to stress too much on it now. We're going to come back to it because you're missing one key concept. Bear in mind, we're going to have a separate video where we go through each of the components and what they do. So don't stress too much about it now. We're going to run through our analogy and work through it. So I've given you that beaker of sodium hydroxide with the unknown concentration. And to find the concentration, you're performing a acid-base titration with the acid hydrochloric acid. And that gives you sodium chloride and water, as I previously stated. Going on from the previous example, you have just added the perfect number of molecules of hydrochloric acid such that every molecule of sodium hydroxide has been reacted with. So if there is, in that unknown beaker, say there's hypothetically 100 molecules of sodium hydroxide, you have added 100 exactly 100, no less, no more, of hydrochloric acid, such that there's no more sodium hydroxide and no more hydrochloric acid. There's only sodium chloride and H2O left in the solution. So do you agree, at this point, the moles of sodium hydroxide and the moles of hydrochloric acid would be equal? I guess that makes sense. And we also know that we can get the moles by multiplying the concentration by the volume. And I've represented that as C1V1 for sodium hydroxide and C2 times V2 for hydrochloric acid. So if the moles of sodium hydroxide and the moles of hydrochloric acid are equal at that point, that means these two expressions are also equal at that point to give you something that like this. This will come up a lot, so bear that in mind. So everything with a 1 relates to sodium hydroxide, which we don't know. Everything with a 2 relates to hydrochloric acid. So just bear that in mind. As I previously stated, let's look at everything with 2 on the right-hand side. You know the concentration of the hydrochloric acid. So you know this because you made it. You got it from a jar, or you got it from a lab. You got it from somewhere. You made up that hydrochloric acid. V2, that is the volume of hydrochloric acid that you added to the beaker such that the moles of sodium hydroxide equals the moles of hydrochloric acid. That's how much acid you've added. So you also know V2 because you added it. C1, I gave you that beaker and I told you to find the concentration. You don't know that yet. You do not know that. V1, you do know the volume. I gave you a beaker. You know how much volume of sodium hydroxide is in that beaker. It's just whatever volume's in it. So you do know that. So you know 3 things and you need to find 1. You can very well do that. So rearrange it. C1 equals C2 times V2 over V1. You have your concentration for sodium hydroxide. And essentially, that is the premise of titrations. Simple, right? Okay, so now you should have a fair understanding of the basic principles of a titration. So essentially, if I were to give you a substance of unknown concentration, in order to find that concentration, you would use a substance that you know the concentration of really well and take it through a reaction that you not only understood, but was predictable. And usually in your senior studies, that's going to be exclusively an acid-based reaction. So you're only going to be doing acid-based titrations. Bear in mind, there are other types of titrations, but for your purposes, just know the acid-based titrations. You'll either be given an acid or a base, and then use the opposite to titrate it, and just take it through an acid-base titration. However, we run into a problem. So I'm going to flick back. So this point here, in which the moles of sodium hydroxide and the moles of hydrochloric acid are equal. How can we tell that we've reached that point? How can we tell that all the sodium hydroxide has reacted with all the hydrochloric acid and no more? So there's no extra hydrochloric acid that we've added. We've added just the right amount such that it's reacted with all the sodium hydroxide in that beaker that I've given you. The answer is an indicator. So if you look at here, initially, that beaker that I've given you only has sodium hydroxide. So it's going to have a really high pH because that's a strong base. Over time, you drip little bits of hydrochloric acid in. Hydrochloric acid is an acid, so it's going to slowly bring the pH down from, say, sodium hydroxide, really high pH, might have a pH of 12 depending on the concentration. You slowly drip hydrochloric acid in. 12 becomes 11, becomes 10, becomes 9. So that pH is going to come down. Eventually, at this point, there will only be sodium chloride and water. Those are neutral substances. They will have a pH of 7. At that point, sodium hydroxide and hydrochloric acid, the moles will be equal. So in order to do this, you use an indicator. When that indicator changes color, so it might go from blue when it's basic. When it changes color, you know exactly then you've reached the perfect point. So what would happen if you kept going and you just kept adding HCl? HCl is an acid. So that pH of 7 that happens at that precise moment, if you add more HCl, it'll just keep going down. So the solution will just keep getting more and more acidic and the indicator will change color again. That means you've missed that point and you're going to have to redo the entire titration again. That's why I said in the beginning, the principles, as you surely have come to understand, are really simple to understand. It's really pedantic. You need to be really particular, have really fine motor skills. Once you nail the technique, it should be fine. So this brings us onto a quick discussion of endpoint versus equivalence point. So essentially the endpoint is a point in which the color of the indicator changes. So that it is literally, that's all it means. The equivalence point, however, is a point in which the number of molecules of the titrant and the analyte are equal. So the titrant is what you're using to titrate. So in our example, it would be the hydrochloric acid and the analyte would be the sodium hydroxide. So basically, it's at this point. So when the moles of sodium hydroxide equals the moles of hydrochloric acid. Ideally, we want these two things to coincide. However, in practice, especially in the ways you're doing titration, it's actually really hard to find an indicator that has an exact change in color in the pH that you want it to. So in our previous example, it changed color at pH 7 because both of the products were neutral. However, as you're going to see, that's not always the case. So it's really hard to make an indicator that changes color at the exact pH of the equivalence point in which the molecules of the titrant and the analyte are equal. However, for your senior studies, just remember those two definitions. That's the most important thing. So I told you I'll come back to the slide and I'll run you through some of the materials. So essentially this first thing here looks kind of strange, but it's a pipette. So that is what we use to draw up an exact volume of our unknown substance because that represents V1. So we use that to get an exact representation of the unknown substance. Usually they're 25 milliliters. They're really cool to use and not only watch our videos that we're going to come out with, but when you're actually doing the lab, keep an eye out for them. They're really cool to use. This thing here is a burette. Bit different. So essentially you can think of it as a really long glass measuring cylinder with a tap at the end. That is what you're going to use to slowly add, in this case, it'd be the hydrochloric acid. You slowly just open the tap, add little bits of hydrochloric acid in. Just remember that we also added the indicator in between these two taps. So this represents the indicator. And as you can see, I add little bits of hydrochloric acid and then suddenly you'll see it just change color. It's incredible. It just quickly just flashes color. Especially if you use a dye called phenolphthalein, it just quickly turns a really lovely pink. So using the burette, we know exactly how much volume of acid that we've added. So if we start here, for example, and then at the end of the titration, there's about this much acid left, this is V2. And then obviously, C2 because it's whatever concentration of hydrochloric acid that you use. Usually it'll just be 1 molar. So as I previously stated, depending on the final products, you will need to change the indicator. Basically, for your senior studies, there are 4 different types of acid-base titrations that you can perform, and we're going to break through each one of them. The first one here is that between a strong acid and a strong base. This will always give you products that are neutral. So in this case, between sodium hydroxide and hydrochloric acid, you get sodium chloride and water, both sodium chloride and water being neutral products. If they're neutral, that means the equivalence point of a titration between a strong acid and a strong base will be that of around pH 7. So for example, this refers back to our analogy of that unknown solution of sodium hydroxide. It will start at a really high pH. As you add more and more hydrochloric acid, you will bring that pH down to an equivalence point of pH 7, in which there is only sodium chloride and water being made. In other words, there will be none of this left because it would have reacted with all of the hydrochloric acid that you've added. The best indicator for a strong acid and strong base titration is bromothiamyl blue, as it crosses a pH of 7, so just remember that. Furthermore, you could also have a titration between a strong acid and a weak base. I should also add that for each of these examples, it doesn't matter what is being used to titer and what is being used as a titrant. So you could have the base as the unknown and using the acid to titer, and the acid as the unknown and the base used to titer. Either way, the indicator selection, as I show you, will stay the same for each given criteria. The criteria in this case is a strong acid and a weak base. So our example of the strong acid, we're going to use hydrochloric acid. And for our example of the weak base, we're going to use ammonia, which is NH3. This will give you ammonium chloride and H2O. The main key to decide which indicator you're going to use depends on the acidic or basic nature of the products. In our last example, they were neutral, but here you'll see it's a bit different. So ammonia, NH3, is a weak base. That means the conjugate acid, so the NH4 part, is going to be slightly acidic. Just reason that out because it's a conjugate acid. Thus, although water is neutral, NH4Cl, so ammonium chloride, will be slightly acidic. So if we use bromothiamyl blue again, as in our previous example, it's going to be completely useless because the equivalence point will be less than 7 in an acid-base titration involving a strong acid and weak base. Thus, we need methyl orange, which is the best indicator for this titration, as it crosses that lower than 7 pH, because, as I said, ammonium chloride, this thing here, will give you a slightly acidic endpoint. In our next example, we have a titration between a weak acid and a strong base. For our weak acid, we're going to use acetic acid as our example, and with our strong base, we're going to use sodium hydroxide once again. This will react and give you sodium acetate and water. Again, although the water is neutral, the product sodium acetate is slightly basic. But why is that? So acetic acid here is a weak acid. So it contributes a conjugate base that is obviously slightly basic. This sodium ion here comes from sodium hydroxide, which is a strong acid. So this sodium will have no properties. No, it'll just be neutral. However, due to the acetate anion here, sodium acetate overall will be slightly basic. Thus, the endpoint of a titration between a weak acid and a strong base will be greater than 7, as it's slightly basic. If we use methyl orange or bromothymol blue, as in the previous examples, it will be completely useless. We need an indicator that has a color change that occurs slightly above a pH of 7. The indicator of choice, thus, between a titration of a weak acid and a strong base is phenolphthalein. This is what you'll use commonly, and it creates a really nice pink color. Titrations between weak acids and weak bases aren't commonly done. So you don't really need to remember indicators that you'll use. However, we'll go through an example of one now. So it's acetic acid being used to titrate ammonia. This will give you the ammonium acetates and water. So the weak acetic acid contributes a slightly basic conjugate base. The weak base, ammonia, contributes a slightly acidic conjugate acid. However, this is just one titration. There is an infinite number of weak acids and weak bases that we could use, like combinations. And thus there are a complete spectrum of pHs, because the relative strengths of the conjugate acids and conjugate bases can differ greatly. So there's not like one indicator that suits all titrations for weak acids and weak bases. If you really want to follow it, you'd probably use a pH probe, in which you literally just dip it into the beaker and you just monitor the pH. This is a high yield summary table summarizing the type of titration and the indicator that you'd use. It's really important that you remember this.